Swayam Prabha. Digital India. Educated India.
Hi, this is Mr. Venkat Rao. I'm going to ask him a question. It's a simple question, don't be nervous. The question is simple. I just have to know there is a body here, okay? Just like what you see here, okay, it has a weight on it equal to mg. I want to know the frictional force on this block. How do you find out? I want to know the frictional force on the block offered by the surface.
Offered by the surface.
Right. Can you write down the magnitude of that? You can come this side. Can you write the magnitude of that?
Unless it is subjected to movement,
But there is a
we don't know
frictional
what is
force.
the frictional force, direction of the frictional force.
But there is a frictional force.
Exactly.
Okay. So what is this frictional force if I apply? I have a weight of mg.
Yeah, we will get exactly opposite to the weight of the.
That's the normal reaction.
Normal
This is the normal reaction. Let's
Okay.
call this as n.
Yeah.
N is equal to mg.
Yes.
What will be the frictional force? If n is the normal force,
Yeah.
the frictional force is related to normal force. Is it
Not,
not?
yeah, friction will be.
Supposing I
there.
am applying a force like this,
Okay.
the frictional force is
Opposite to the direction of the applied force.
which is equal to mg is given.
0.
No, no. What is the frictional force? If mu is the
Mu mg.
write it down.
Yeah. Suppose the body is moving that direction.
No, no. Supposing I am applying a force here,
Okay.
the frictional force
Will be
here
opposite
is
to
related to this.
Coefficient of friction into
Write it
the
down.
weight of that. Mu mg.
Very good. Okay. Thank you.
Thank you.
Often this is the mistake many students make. Okay, I am not pinpointing one student. Most students will immediately write the frictional force to be mu times mg, which is, I am going to argue or discuss that this is not always the case. Okay. So, let us just look at it more seriously and understand this particular problem. So, let me start off with a simple idea here. Let us say this is the body, there is a weight acting on it, and if I draw the free body of this, am I audible? If I draw the free body of this, then mg is acting like this, there is a normal reaction n, that much is correct. When I apply a force, let us say like this equal to F, the question I am asking now is what is the frictional force? Yes, the answer is partially correct. The frictional force is opposite to the force applied, but saying that this is equal to mu mg is not always correct. This is the notion that many students have a problem with. Okay. Of course, in this particular case when I say mu s is the coefficient of friction that I am talking about, static friction. This is true only when the body starts to move or is about to move. Okay. So, if I draw the frictional force F versus the actual force applied like this, mind you I am applying at the bottom so that it is easily understood that these two do not form a couple. Okay. What will be the force here? Supposing I apply let us say 5 kilonewton over here, let us say that is less than mu times mg, what will happen is this is the 45 degree, line, which means that the F is equal to capital F in magnitude, okay. But when it reaches a particular value which is equal to mu times mg, that is when the whole thing changes. The frictional force cannot be above that particular value, okay. Let us assume mu static is equal to mu kinetic, okay, just for now, so that the argument is simple, the discussion becomes simple. So when it reaches this particular value, please remember the frictional force cannot increase at all, right. Can the force F increase? It can increase, supposing it goes like this. What happened to the additional force that has been offered? The additional force offered goes towards accelerating the body. Is this understood? This is very important. So if I am looking at static situation, it is only one instant when F is equal to mu times mg, that is at the threshold of starting to move. So when I have this body and I am applying a force, okay, for it to move I need to apply a force that is equal to mu times mg for it to start move. When it starts to move, mu kinetic, coefficient of kinetic friction will play a role, okay. This is often a mistake that students make, and please remember small f is equal to capital F comes purely by equilibrium. If I look at this free body and find out, let me write it down here, sigma f along x direction, if this is x direction, let us say this is y direction, is equal to 0 for static condition. Immediately I have only two forces taking part, this is capital F, this is small f, means capital F minus small f, because the direction is negative to this, is equal to 0, which automatically tells me that capital F is equal to small f. When is this true? It is true only when the right hand side is 0. What is right hand side? It is nothing but saying that it is in static condition. Supposing it is in dynamic condition, then F equals ma, which means that sigma Fx should be equal to m times Ax, right. So if I insert these values, I have capital F minus small f is equal to m times Ax. When Ax is equal to 0 at the static condition, this is equal to 0, capital F equals small f, but if Ax is non-zero, okay, in the condition when it is non-zero, remember this, there is a motion involved, which means this reaches, so in motion or at impending motion about to move, then F is equal to mu times mg. What is this? This is the property of the surface, the two surfaces that interact with each other. This has nothing to do with equilibrium, unless I am told F equals mu mg, it is indeterminate, right. Once I know it is mu equals mg, then I can write F is equal to m times Ax plus mu times mg. So part of the force is taken by the frictional force and part of it goes towards accelerating it. This is a very crucial point that has to be understood. There is one more point that is very important. When I asked Mr. Venkat Rao, he immediately answered that if I apply a force like this, the frictional force will act opposing the motion. Please remember the statement I am making. Let me go over there and write it down. frictional force is acting in a direction let me come back to direction. Supposing this is the body and let us say this is the force acting. He said that the frictional force acts in the opposite sense. Okay. Now, I am going to twist it a little bit. I have F1 acting like this, okay, F2 acting like this, F3 acting like this. Now, tell me what is the direction of F, small f. So, a simpler way of looking at it, what he is saying is it is opposing the resultant of this. A simpler way of looking at it is it is actually opposing not the force, but the motion. It is the resistance to the motion, or in other words in a direction opposite to the motion or impending motion of what? Of a surface on a surface, of a surface which is this surface, on a surface which is this surface. This is on, this is off. Is this clear? This should be understood clearly, which means what? If I have a body, so let me just make it very clear to you in this scenario. If I have a body like this and I am applying a force F, and if I say the impending motion is in this direction, I will apply a force, frictional force. Since the impending motion is in this direction, it should be opposing it. I will put this F. Since it is impending, it has reached the maximum value, alright. I can turn around and say, what if this is negative? I am pushing it a little bit and then I am pulling it. Remember, when I pull it, again once I reach an impending motion in the opposite direction, if the impending motion in this is in the direction, then F equals F will act in this direction, okay, and this should be understood, which means between a force that reaches mu mg in this direction and a force that reaches mu mg in this direction, the body is in static equilibrium and the frictional force changes from positive value to negative value. So, if I plot this F versus the frictional force, when I am applying in this direction, let us say it is positive, it will keep on increasing, this is F till it reaches mu times mg, alright. Similarly, if I move in this direction, if the impending motion is in this direction, till the motion occurs, it will keep on decreasing. Again, when it reaches a particular point, mu mg, in this case minus mu mg, it will not be moving. So, between this and this of the region, so if I have this value and this value specified, this is mu times mg, the reason is this is at a 45-degree angle. This is minus mu times mg. So, when the force is within this region, when the force is within this region, it is in static equilibrium and the small f is equal to capital F, okay. Beyond this there is motion, beyond this there is motion in two different directions, Is that understood? Third point, supposing I have a block like this, okay. This is again a mistake that is often made by the students. So, I just want to point out such a mistake. Let us say a homogeneous body mg is acting like this, there is a force acting like this F, basically I have something like this and I am applying a force like this, okay. I need to now draw the reaction forces. Well, that is very simple, one might remove this. Well, where is the normal reaction? Here. Where is the frictional force? Since it is opposing motion in this direction, is equal to F, okay. If it is static, this is equal to this, okay. That condition of F is static is very important. The condition of motion is a different story altogether, fine. The answer is not correct, this is not correct. Most of the students who are used to drawing this from physics get confused. Unless this force is over here, you will see what is this equal to? This is equal to capital F, which means this and this form a couple which is like this. This is the height h, F times h is a couple that is acting. Where is the resistance to that couple? The resistance is offered by a variation. For example, if I draw the normal reaction to be uniform like this, then its resultant is along mg. Actually, since I have to offset this couple in the static case, it will actually n will shift like this, so that this will form an opposite couple, alright. This is equal to mg, n equals mg when I find the vertical equilibrium, and the distance between these two is such that it is equal to Fh divided by mg, or in other words mg times this distance will offer the opposite reaction. What is this n? This is the net resultant reaction that comes from the pressure that is offered by the surface. So, this is a resultant, please remember that. Sometimes when I cut like this, one of the mistakes people do is they will say okay, n is acting like this, there is no n here. This is nothing but a representation of a distribution of this sort, the resultant of which is what is drawn like this, okay. So, when I cut like this, I will have this reaction coming into picture, okay. This is the third mistake that is often made. With this as the basis, most of frictional problems can be solved, okay. So, let us take up one problem which is often used in friction type of applications. Where all do we encounter friction, where all do we use friction to our advantage, where all do we encounter a problem with friction is often already talked about, okay. One of the acute applications in which friction is used positively is a belt drive. What is a belt drive? Let us say I have a motor over here, okay. The motor has a roller over here, rotor, and this that is rotating. I have another, let us say this is a wheel, I need to rotate this wheel. So, what do I usually do? I connect this with a belt. Let me draw it with another color. I connect it with a belt, okay. So, what is basically happening is when this is rotating, the friction between the pulley and this. So, here when it is rotating, the belt has a friction on this rotor that takes it up along the belt transfers that friction through this, so that this rotates when this rotates. Okay. There could be slipping, there need not be slipping. The two conditions are handled very similar to handling motion and statics over here. Okay. So, let us do this kind of a problem, because this is one of the problems that we will encounter in mechanical engineering and similar engineering applications. The aim is to find out, supposing I fix this, okay. So, I fix this and I apply a force over here, tension over here, say T1, let us say it is in motion, okay. What is the tension in this? Is this clear? This is not moving, I am pulling this with a tension T1. What do you realize? Is T2 less than T1? The answer is yes, because there is some friction that has eaten away some of the tension. T2 will be less than T1. Can I find out T2? That is the question. Okay. Let us answer that question. Why is it important? By answering this question, I will be able to tell you, depending on T1 and T2, whether slipping has occurred in this or in this. If no slipping has occurred, then the entire thing is transferred directly to this. This is usually called the effort and this is the load. You do not want the power to be wasted in friction, because friction is going to convert it to heat and there is a loss of energy unnecessarily, okay, in addition to the other losses that you encounter. Okay.